Let's start with the second part of this morning's tutorial. My name's Adam Smith. So I'll be picking up where Aaron left off, and I'll be repeating just for the first few minutes. I'll kind of recap where we were, just to make sure everybody's on the same page, and also because my notation is like a little different from Aaron's in the slides, so just to make sure everybody can follow. But basically, in some sense, what the theme of this part of the tutorial is going to be is it's about the benefits of hiding the data from the analyst in various ways. Okay, and I'll talk about sort of three related notions of what we can mean by hiding the data. We'll talk about differential privacy, sort of slightly more general notions of algorithmic stability, and then various kinds of information bounds. What all three of these notions allow us to do is to relate some sort of this adaptive setting that Aaron was talking about, in which you've got an analyst asking questions in sequence and asking those questions and trying to have those answered on the same data set, to some sort of statistical ideal in which each time I ask a question, the question will be answered using a fresh sample from the same distribution. Okay. And in some sense, these three tools get at different ways of kind of matching these two settings and relating them so that we can get the kinds of guarantees we want, the kinds of guarantees we would get in this kind of statistical ideal setting in this adaptive setting. And as Aaron mentioned at the end of his tutorial, the larger goal here is to develop some sort of not only a descriptive theory of understanding, when do we overfit, when do we not overfit, but also some sort of prescriptive theory that tells us gives us, ways to design algorithms and estimation procedures and analysis workflows that maximize the sort of long-term analytic and statistical value of the data sets we have. Okay, so I will, as Aaron did, I'll spend a lot of time talking about this problem of adaptive linear queries or adaptive statistical queries, both because it's an important problem on its own, but also because it's kind of simple and clean enough that it's a good playground for understanding the tools we have. And even though in the literature that I'll be mentioning, there's lots of other models that people have looked at, I'll just stick to this because it'll keep the discussion more focused. So imagine we've got this, again, an analyst outside. So we've got a data set X that is drawn from some unknown probability distribution. We've got an analyst asking questions and some algorithm A that is trying to help the analyst answer these questions. And it's useful to kind of think of this process that's answering the questions as separate from the analyst, even though in reality they're really the same, often the same person, not always. Okay, so what's a query here? It's a function from some domain X to 0, 1. And there are sort of several relevant quantities given this data set X and this distribution P, several quantities that we're going to try to relate to one another. There's the empirical answer, so that's just the average of this query over the data set. There's the population answer, so this is the expectation of the query on a fresh sample from the same probability distribution. Or if we think of the population as just an actual population of people, then this would be the average over the population as opposed to over the sample I have. Okay, and I'll sometimes call this empirical answer the sample answer, this population answer, or distribution answer. And we'll say that this algorithm provides answers with error alpha if for every query the answer provided is within alpha of the actual population mean, okay, with some high probability. And I'm going to sweep almost all of the high probability stuff into the O tilde notation. Okay, so these types of queries capture lots of basic analyses. If you think about like contingency tables, for example, or marginal distributions, they can be represented as a sequence of such queries. Classification error of a candidate classifier certainly fits this kind of model, and also a lot of more sophisticated optimization algorithms. For example, gradient descent can be thought of as an adaptively chosen sequence of queries of this form. And in fact, there's a number of recent papers, I think John Ducci will talk about one of them, on trying to understand just to what extent adaptivity is actually necessary in these types of algorithms. I don't know if that's what you're actually going to talk about. Good. All right, so there's the plug. Okay, so one question we can answer that, or ask that will kind of propel us forward in sort of trying to understand the tools what the tools we have give us, is to aim for a kind of a minimax theory of this setting to try and understand just how small we can get alpha for a given probability of success, and to understand both upper and lower bounds on the error that one can get in these types of settings. Okay. So again, what we want, as Aaron said, I don't have all the quantifiers here, but what we want is to understand the worst case over distributions and analysts of the accuracy of the algorithm, where the algorithm gets a sample from the distribution. So as Aaron mentioned, if we're asking non-adaptive queries, if we just sort of if the analyst is not actually looking at the answers AI to come up with subsequent queries, then we get a very clean bound. We get this sort of essentially 1 over square root of n type behavior, and there's some mild dependency on the number of queries. On the other hand, what Aaron convinced us is that if we're answering queries in the simplest and most direct way, which is to just answer via the empirical answer on the data set, then what we get is something more like square root of k over square root of n. And in fact, we'd get a similar scaling, or essentially the same scaling, if we were to approach things a little differently, to just chop the data set into k pieces of the same size and answer each query on a fresh chunk of the data set. So that would certainly give us nice analytic guarantees, but the chunks start to get small once k gets big. Okay, so what can we do is there anything we can do in between? So Aaron started to provide answers to this. In fact, okay, so in this, there's sort of a sequence of 3 papers by the same authors, so Cynthia Dwork, Vitaly Feldman, Moritz Hartz, Tony Patasi, Aaron Roth, and Omer Reingold, or maybe Omer Reingold and Aaron Roth, that appeared in 2015. They gave a lot of this tutorial is based on those papers, and they gave one bound, which is of this form. There is a lower bound, which is sort of incorporates these same terms, but shows us that a polynomial dependency on k is in fact necessary. And so that's a really nice work by, well, it started with the paper of Hart and Ullman. This bound, the specific bound comes from a follow-up paper of Steinke and Ullman. And then refining the techniques in this paper of Dwork et al., Raif Basili and others, including myself, gave an improved bound of about 4th root of k over n. And in fact, there remains a gap in our understanding of the exact error that we can achieve here, although there's sort of good reasons to think the right answer is this 4th root of k over n. So these are kind of bounds on the accuracy. It's a little easier to compare them if we say fix alpha and say ask what's the sample complexity that we need to achieve these bounds, and then we still get this sort of square root of k everywhere, but then it's sort of more easy to understand the progression that's going on in these various results, which is really it all comes down to this dependency on alpha, on how accurate we want the queries to be, and basically what we get is that the kind of current open question is exactly what exponent do we need? How does the sample complexity scale with the accuracy we want? But what we do understand very clearly at this point is that we really need to pay a significant cost in the worst case for asking lots of queries. The square root of k term is known to be necessary. Okay. So that's just a quick overview of the known bounds, and now what I'll try to do is give you a taste of both the tools that go into these bounds and also subsequent developments. Okay, so the first part of the talk, real part of the talk, will be called privacy, stability, and generalization. Pick any three, and I will explain what I mean by that. But roughly speaking, what we'll see is that, as Aaron mentioned towards the end of the talk, his part of the tutorial, stable algorithms don't overfit. And we'll think about how to use that idea. Okay, so one of the key tools that we'll be thinking about is differential privacy. So I'll repeat the definition from Aaron's talk. So imagine we've got a data set. It's a set of values in some domain. Sorry, that should be an X. This domain could be numbers or categories or anything. It could be arbitrarily complicated. But for the purpose of the definition, we'll think of the data set as fixed. So it'll be worst case over data sets. And then we'll think of the process that analyzes the data as randomized. And our guarantees on information and stability and things like that are going to come from the randomization that this algorithm does. Okay. So we'll consider a thought experiment where we imagine changing one person's data, or they don't have to be people, one of the data points in the data set. And the question we're going to ask is sort of, how sensitive is this process, this algorithm that's answering questions, to changes in the data? And specifically, what we want to know is sort of not so much, these aren't so much questions of numerical stability, of like how much does the answer change as a number, but rather how much does the distribution, how does the distribution on outputs change? Okay. So a little more formally, we'll say that data sets X and X prime are neighbors if they differ in exactly this one data point. And the requirement, our definition, will require that neighboring data sets induce close distributions on the outputs. So specifically, an algorithm A is epsilon delta differentially private if for all neighbors X and X prime, and for all possible subsets of events. For all events in the output space, for all subsets of outputs, let's say these subsets have to be measurable, but we're going to ignore that. The probability that the output lands in a given subset when the data set is X should be close to the probability it lands in that subset when the data set is X prime. Where closeness is measured by two parameters, a multiplicative parameter, which can in general be reasonably large, like say 1 over square root of n or something like that, and an additive parameter delta, which will generally be very small, much smaller. So this is the definition we're going to work with, and we'll sort of see various statements about it. But the right way to think about it in the context of this tutorial is as a special case of a very general notion of algorithmic stability. Okay. So given some way of measuring how different two probability distributions are, we can say that an algorithm is stable with respect to that way of measuring distance or divergence between distributions if for all data sets, if I change one entry of the data set, the change in the induced distributions on outputs is at most this parameter rho as measured by that divergence. Okay, so A is rho stable with respect to a particular measure of change if the distance between these two distributions is at most rho. Here, D could be something like Kolbach-Leibler divergence. It could be chi-square divergence, chi-square distance. It could be a Renyi divergence, or a number of other things. And I won't get into too much of the sort of various notions of stability that people have used, but I'll try to point them out as they go. But sort of certainly when you get down into the technical details, and certainly when you're working out concrete bounds of the form John was asking about earlier, then all these different notions of divergence really start to matter. Okay, so why do we consider distributional stability? Why is that like a useful concept in this context? Well, as we say, we want to understand. We want to kind of control what's going on when there's an analyst asking questions and we have no idea what's going on in the analyst's head. Okay. And so there are really two key properties we're going to use heavily about distributional stability, at least when this notion of distance or divergence is chosen correctly. One is that it's generally closed under further processing by other functions, and in particular by the analyst. Okay? So if we've got an algorithm A which is stable according to some notion of the form I had on the previous slide, then it's usually possible to prove that the output of an analyst who sees the output of A also satisfies the same stability guarantee, or possibly stronger. So for example, in particular for differential privacy, if A is epsilon delta differentially private, then so is the composed box B. And the other point that Aaron mentioned is that these notions of distributional stability tend to degrade gracefully when algorithms are composed in sequence. Okay? So for example, if I've got a sequence, if I've got an analyst that is calling a sequence of adaptively chosen algorithms, so at each stage the analyst chooses the algorithm that'll be run, then sees its output, then chooses the next algorithm to run, and so forth. If each of the algorithms that the analyst chooses is epsilon delta differentially private, just ignore the i's, just imagine they all satisfy the same guarantee, then roughly speaking, the whole box, this whole entire process, which outputs the conversation between the analyst and these algorithms, is going to be about epsilon square root of k differentially private. Okay? And other notions of stability, with other notions of divergence, will yield similar statements. And often the usefulness of a particular stability notion when you're proving a particular theorem is going to come from exactly what kind of composition guarantee it provides. So I won't list them all, but that's just something to look out for when you're reading these papers. And it'll come up, I think, for example, in Vitaly Feldman's talk. Okay, so let's just look at an example of something that is differentially private, just to make everything very concrete. Suppose we've got some summary of our data set we want to release, perhaps the answer to a statistical query, but it can live in higher dimension. For example, I don't know, maybe the proportion of diabetics in the data set. So now each person's data is just a bit, and the function we're interested in is the average. One simple way to introduce randomness to the process is to add noise to the value of the function. The question is, how much noise do we actually need? And it turns out that a good way to think about it is to kind of measure some sort of Lipschitz coefficient of the function we're interested in releasing. Specifically, we can ask for the global sensitivity of the function, which is the maximum over neighboring pairs of data sets in the difference between f of x and f of x prime is measured by some appropriate norm on the outputs. L1 norm works well here. Okay, so it's a measure of how sensitive f itself is to changes in its input. And for the proportion of diabetics, or indeed any statistical query, the sensitivity is 1 over n. Because if I change one of the terms in the sum changes by 1. The average changes by 1 over n. Okay, so it turns out that this global sensitivity is indeed kind of the right measure of how much noise we need, at least in general. So if we take our compute f of x and add Laplace noise proportional to the global sensitivity over epsilon in each of the components of the thing we're trying to release, then we indeed get an algorithm which is epsilon 0 differentially private. We don't even need the delta parameter. Okay, what's this Laplace distribution? Well, it's kind of like a Gaussian distribution, but it's a little pointier at the peak, and the tail goes down a little less heavily. Just proof by picture, the reason that this thing is differentially private is what we're doing when we change one data point in the data set. What we're considering are two versions of this Laplace density function that have been shifted relative to one another by the global sensitivity, or maybe the global sensitivity over epsilon. And it turns out that point for point, the ratio of the blue and the red curves is bounded, and so we can bound how much the probability of any event changes. So this is one way to satisfy this definition of differential privacy. In fact, there's this at this point lots of other algorithmic techniques. In addition to noise addition, there's various kinds of ways to use exponential sampling. There are a bunch of other things. There's a whole other class of algorithms based on sort of local perturbation. But the point is that if we develop sort of general tools and theorems that relate properties like differential privacy to generalization, then we get to use this whole toolbox when we're designing algorithms. Okay, and I'll try and give you some flavor of how that works. Okay. So now let me try to formalize this idea that stable algorithms can overfit and give you a sense of how we could use that. Okay, so the final reason why we want distributional stability, in addition to kind of composition and closure and post-processing, is that in some sense distributional stability gives me protection against overfitting. So consider a game between an analyst and this algorithm. So what the analyst is going to do is choose a distribution P on the data, and then a data set will be sampled, which the analyst doesn't see, and handed to the algorithm. And what the analyst gets is the output of the algorithm on this freshly sampled random data set. Okay, and the analyst will now produce a statistical query. And the analyst's score in this game is going to be the difference between the value of the statistical query on the data set and the value of the statistical query averaged over the underlying distribution. So you can think of this as an overfitting game. Imagine we've got this malicious analyst to model, the worst possible case, who is trying to come up with like as nasty a query as possible. And of course, this is sort of the same thing as asking the difference between the value of the query on this data set and the value of the query on a freshly sampled data set from the same distribution. Okay, and so what I would say, one of the key insights of this, the first of these papers by Dwork, Feldman, Hart, Patasi, Roth, and Reingold and Roth. Sorry, it's hard to keep the R straight. Is this connection between stability and generalization? They proved a specific one for differential privacy. But there have now subsequently been a number of results like this that have been formalized, and they have the flavor that is, if A is sufficiently stable with respect to some appropriately chosen divergence, then for all probability distributions and for all analysts, the score of the analyst in this game is somehow bounded based on how stable the algorithm is and the measure of divergence we're going to use. So this is just the same picture as before? Yeah.
I guess the language confuses me.
Sure.
You're using the term query. That makes sense in terms of differential privacy. But when you're talking about overfitting and analysis, what should I translate in my head the word query to? So in other words, I'm someone who's trying to come up with a machine learning model, let's say, like the example that Aaron gave. And I'm Google or whatever. Mm-hmm. And I'm cheating.
I hear Baidu has more power.
And sort of the danger is that I'm overfitting. So this thing that I'm applying, this hypothesis F, right? This it's very confusing. to me to use the terminology of query in the world of analysis. Could you tell me what I...
Yeah, so let's see. So I think you hit on a good point that in some sense, one of the things that's going on is that we sort of considered this setting of statistical queries because it seems like it's for the reasons I mentioned. But why is that a kind of a reasonable way to try to capture what's going on in a lot of statistical analyses? So it isn't always is the first answer, but one of the reasons it comes up is a lot of the statistical estimators that people want to run can be expressed as in terms of you can rewrite the algorithm in terms of a sequence of query. You can ask, how does the algorithm that actually computes the estimator touch the data? And very often you can rewrite the algorithm in terms of a sequence of you can sort of factor the algorithm out. Yeah?
That's exactly what confuses me. You said a single query is a sequence of queries. So when I think of an algorithm, I think of a sequence of queries, right?
Yeah, so inside the algorithm there may be either one or a sequence of queries. So let me give you just some simple examples. So suppose that I'm the Census Bureau and I am trying to publish a bunch of tables about where people live in the country. That you can think of that as a large set of statistical queries, which are not really chosen adaptively, but chosen once before the decennial census is run, and then they're all computed, and the sort of algorithm that the census is running is just going to compute all those queries, find their answers, and publish those values, or perhaps some noisy version of them these days. On the other hand, you can imagine a single algorithm such as gradient descent, where what's going on is at each, so the algorithm itself is going to proceed in stages, and at each stage of the algorithm, it's going to estimate the gradient of some loss function on the data. And if you look at what that sort of computation looks like, it's a sum over data points of each data point's contribution to this gradient. And so I can sort of write the algorithm as itself, like I can sort of refactor the algorithm, if you will, in terms of, here's the data. And out here is some, some process controlling the algorithm, and it's submitting, I don't know, points. Let's call them W, and it's getting back estimates of the gradient of the gradient at W of some loss function defined by the data set. Okay. So I'm not sure if I'm providing the best answer to your question, but so now I can imagine is like, gradient descent is like this whole thing, but I can abstract it out a little bit by breaking it into two pieces. There's the sort of the control piece that decides which points to query, and then there's like the part that actually holds the data that answers, sometimes called the oracle, that actually answers the questions.
Good.
So I hope that was helpful, and yeah.
So if you're thinking about this, whoever it is that you're trying to keep honest, they have to show you how their algorithm can be translated to this thing and how they answer their own queries in a
right. So applying this particular framework that I'm talking about requires sort of thinking about what, in fact, the estimation process you want to use is doing. Okay. By the way, this whole framework applies also equally well when I've got many different people using the same data set, which is, I think, where it really becomes useful, such as the machine learning competition. And there, that sort of factoring into separate processes is already provided. ImageNet is the algorithm that is answering queries, and the analysts are the people out there submitting. The control process is the people competing in the competition who are submitting candidate classifiers and getting back answers. Okay, or imagine I've got like the ad health data set is this like data set that is used by it's about a big data set about adolescent health. One data set, something like 4,000 papers, each of which possibly is the analysis chosen in paper I was chosen based on reading papers, some subset of papers 1 through I-1, maybe going to some talks, So then there's all sorts of complex dependencies. You can think of lots of other examples. Okay. So just instantiating this theorem, we get a sequence of lemmas. For differential privacy, we get a statement of the following form. If A is epsilon delta differentially private, then the score of the analyst in this game is bounded by 10 epsilon with very high probability. We can also get, and this is the theorem where we're going to use this theorem a few times, but I just want to mention there are sort of similar theorems for other notions of stability. For example, if we have stability in the total variation distance, this is the usual, what for computer scientists is the usual statistical difference on distributions, then what we get is sort of a weaker guarantee. What we can prove is the expected score is going to be about epsilon, or order of epsilon. And I don't really know where this first appeared. I first heard this from Frank McSherry, but it's sort of I'll show you the proof. It's kind of a classic thing that goes back to the 70s in some sense. Before Frank was born, yeah. Another kind of one that comes in handy a lot that gives very clean bounds is if you look at stability in the Kullback-Leibler divergence, then what you get is a bound on the root mean score of the analyst in this game, again, about epsilon. And that, I'm not sure exactly where the first place that appeared is, but roughly it comes from this paper of Russo and Zhou. I apologize if I'm screwing up the references. And then there's the version of this that another thing that comes in handy for concrete computations, but I won't go through, is what's called concentrated differential privacy or zero concentrated differential privacy. And it gives sort of essentially this type of statement, but with, in some cases with better constants. Okay, so these are the kinds of statements that people use. And I'm going to prove one of them. I'm going to prove for you the second bullet. And then I'll just give you an idea of how you can use that to prove a statement like in the first bullet. So what's the thing we want to prove? If we've got an algorithm that's stable in total variation distance, so that means if I change one input, its distribution changes very little in statistical difference or total variation. Then for all distributions P, we get the following. If I choose the data set from P, IID, and I choose the output of A based on X, and I look at the expected difference between the empirical answer and the population answer, then that expected difference is small. Here's the proof. I'm going to first let's fix the distribution P without loss of generality. So the analyst chooses that. We'll just condition on P being whatever it was. And we're going to consider, we're going to compare the two distributions on two triples of values. Okay. So the first triple is our data set together with a random index I. So sorry, I guess that's missing. So I'm going to imagine the first data, I've got my data set X. I've got an index I, and then I've got A of X. And I'm going to consider an alternative, sort of an alternative reality in which in the data set, I'm now going to sample. So here's my initial data set. What I'm going to do is I'm going to sample a fresh value for position I of the data set. And I'm going to replace that in A's. I'm going to replace A's input with, instead of giving it X, the real X, I'm going to give it almost the real X, but exactly one entry will be changed. Okay. Now, what stability in total variation gives us is that the distance between these two distributions, the distribution on this triple and the distribution on this triple, where everything is sampled IID from P, that statistical difference is at most epsilon. Okay, so it's sort of not hard to prove. Basically, you're using some convexity of total variation distance. All right, so why is that a useful thing? Well, what does total variation distance tell us? It tells you if you take any bounded function on a random variable, then if you change the random variable in total variation distance epsilon, the expectation of the bounded function will change by at most epsilon. That's like a definition of total variation distance. And so here's the specific function we're going to look at. We're going to look at taking, so this function takes a triple, x, I, and some value. We'll call it y. We'll take the value y. We'll choose a query based on it. We'll run the analyst. So the analyst has been baked into F at this point. And now, but we will evaluate this query at exactly one point, which is the ith coordinate of x. All right. So total variation distance is about expectations. Let's evaluate the expectations. In the first case, when I evaluate this expectation, what am I getting? I'm running A. I'm picking a random index in X, and I'm evaluating F. I'm evaluating Q of A on that random index. In expectation, what I get is the average over X. Okay. So what I'll get in expectation is exactly like the first term up here. On the other hand, in the second world, where I've like replaced just this one data point, then what's going on is I'm computing A according to the same distribution I was computing it before, except now I'm evaluating my query on some sample from the distribution that A didn't get to, that A never was involved with. Okay, and so now in expectation, again, what I'm going to get is not the value on the data set, but the value on the underlying in the average over the population. Okay. Now, if my algorithm didn't satisfy this type of stability guarantee and its output like was really sensitive to individual data points, these two distributions could be wildly different. Okay? But because we have a stability guarantee, we know that they can't be that different. And so in particular, these two expectations are close. They're off by at most epsilon. And so by linearity of expectation, we get the lemma. So this is a very simple proof, I think. But it basically gets at why this stability property is useful. Now I cheated, actually. The lemma I stated on the previous slide was actually about the absolute value of this expectation, the expectation of the absolute value. And what I just bounded was the absolute value of the expectation. Just ignore that. Okay. Pay no attention to the absolute value behind the curtain. All right. But this, I think, just conceptually, this is the proof to have in mind. So in fact, to get this, yeah, you need a little more work to get the absolute value in the right place, but I'm not going to do that. Okay. So that gives you some sort of bound on expectations, but in fact, what we want, bounds on expectations are very weak. We want high probability bounds on generalization error, and we need them in a number of applications. And it turns out you can get essentially sub-Gaussian style concentration, but then you need more than just total variation stability. You need to go a little further. Generally, the best things we have asymptotically are based on epsilon delta differential privacy. And the idea of how these are obtained is what came to be called the monitor technique, or version 1 of the monitor technique. And this is due to Kobe and Uri. And the idea is I'm going to sort of amplify, to get a high probability bound, I'm going to start with an expectation bound and then like amplify probabilities somehow. So I'm going to imagine that I've got an analyst that succeeds with some probability delta. And I'm going to show that delta can't really be too big. And the way I'm going to do that is I'm going to consider running 1 over delta independent copies of this little overfitting game. And then I'm going to use some differentially private algorithm to select like the worst performance from the mechanism's point of view, or the best performance from the analyst's point of view. And I'm going to argue that, so now I've got this sort of composed process where I've got a bunch of independent copies of this game, plus some monitor on the outside that is choosing, differentially privately choosing the best, the interaction where the analyst got the highest score. And what Newsom and Stemmer show how to do is to argue that this composed algorithm, first of all, is differentially private. So that's easy, that you just use the composition for differential privacy. And where the privacy guarantee has no dependency on T. It just depends on the original properties of the algorithm. And then there's a sort of a more subtle thing that they prove, which is that they extend this expectation bound that I had on the previous slide to show that when the algorithm is differentially private, the algorithm in expectation should not be able to overfit to any of these T data sets. Okay, so I'm not going to formalize this part. This part's like, this is sort of where the magic happens, and it requires a calculation, but like that's the, in some sense, the crux of the proof. Oops. But yeah, so the idea is we get sort of high probability bounds by some kind of amplification, a proof by contradiction. We assume that there were an analyst that could exceed the bound with probability, 1%. We run 100 copies of this game and show that actually, if the analyst could succeed in each execution, probably 1%, then overall in the composed game, the analyst would succeed a lot of the time. And that's the thing from which we derive the contradiction. Okay. So what has this got? Oh, right. I wanted to say one more thing before we wrap up. Okay. So there's another thing about this proof that I wanted to point out to you, and this comes from a paper. This way of phrasing it, I think, it was made to me clear to me in a paper by Somesh Jha and Matt Fredrickson and some others, although it probably appears elsewhere. But in some sense, what this tells me is like, sort of privacy-style properties imply generalization, but in vice versa, that's almost like a tight characterization of generalization. Like, if I've got something that generalizes poorly, where it's possible to come up with a query that makes this difference large, then exactly what I've done is to find a place where to find an algorithm that's somehow paying attention to individual data points, and telling me a lot about like one person in the data set. And so these sort of properties are kind of very, very tightly linked. Okay, so let's try and use this to do stuff. Again, here's our picture from before. What we want to do is understand maybe like this bound. And also I want to connect it to the kinds of things that Aaron was talking about, the kinds of algorithms based on compression that Aaron was talking about in the previous part of the tutorial. Okay, so to do this, what we'll do is we'll sort of take that generalization bound, which applied to just a two-stage game, like a game with exactly one kind of interaction with the analyst, and I want to kind of generalize that to more interactions. So the lemmas we had before, connect accuracy on the population with sample accuracy. Now what I want to do is get something useful for answering statistical queries, lots of statistical queries. So to formalize it, we'll say that the algorithm A is alpha beta sample accurate if its worst case error, if for every particular data set it might interact with, and for every sequence of queries, with high probability, it's giving answers that are accurate for the data set X. just what means, that's what sample accuracy means. And the nice thing about sample accuracy is that it's sort of easy to prove because there's sort of much less probability involved, right? There's no, that you just got one data set, you write it down, it's a worst case thing. The sort of general connection between sample accuracy and privacy is that if I've got an algorithm that's differentially private and it is alpha beta sample accurate, then indeed the worst case, the worst general population error taken over all the queries is going to be bounded by alpha plus epsilon, where alpha is the sort of error on the sample and epsilon is the stability guarantee, okay, with some probability. Okay, and there's sort of similar theorems that are possible for weaker stability notions, although they generally give you, like, you know, weaker or different probability guarantees. Okay, so how do we get this? So intuitively, this sounds like a direct application of those sort of previous lemmas, but there's actually a hitch, which is that somehow what we need is we need a good way to handle the fact that there could be many, many rounds of back and forth conversation between the analyst and this algorithm that's providing answers. And in some sense, that is going to be, that it turns out that will actually be very simple to resolve, but sort of is the crux of the proof at this point. So what the lemmas we had in the previous slides talked about was sort of what happens with just two steps, where I ask a query, get an answer, ask a second query, get an answer. Now I want to kind of lift this result to k steps. Okay. So the simplest way to do this would be by induction, right? Everybody likes induction. One thing we could do is sort of imagine that, you know, we're going to view this as a sequence of two-stage games. And so to understand how much I can overfit at the ith stage, I'll just think of the algorithm that processes the first I-1 queries as one big chunk. It gives some output. The analyst chooses the ith query. And, you know, you can bound how much the analyst overfits. And then what you can do is basically just take a union bound over all these different rounds. And if you just add up the probability of getting a bad query at each round, then you'll get a final bound on the probability that you ask a bad query at any time. But the problem is that then you get this dependency on k, this linear dependency on k in the probability of getting a bad query. Okay, and so it turns out there's sort of a second way to use this sort of outside monitor idea, which works very well here, which is instead of trying to analyze things as a sequence of interactions, we'll just look at the whole interaction as one big piece. And we'll imagine an algorithm, a sort of a meta algorithm that includes that sort of runs the analyst, runs this interaction, and knows the distribution p. And what this sort of monitor algorithm will do is, at the end of the interaction, they'll take the worst of all the queries that was asked, and it will return just that query as its output. So this is sort of a kind of like that what was going on in the high probability argument, but sort of different, because now I've just got one data set. So now what we can do is now we can just say, like, well, how does this algorithm do at overfitting? Okay, and because we know that this algorithm overfits, you know, won't overfit in either like in expectation or with high probability, then that tells us about the kind of the worst interaction that could have occurred over the entire sequence. And in terms of so this yields much stronger bounds on you know, the error. And another nice thing that I'm not really going to go into is that it generalizes beyond these linear queries. This type of argumentation gives you more. And also it gives you, it means when you're working with weaker stability notions like KL stability, often this makes a huge difference in the kinds of results you can get. So let's use these sort of tools we've developed for this transfer theorem. Okay, so one question is, you know, what happens with worst case adaptively posed statistical queries? Well, the thing we're going to use is that, so the thing we want to prove is that one can answer an arbitrary sequence of k adaptively chosen statistical queries with error, as I said, fourth root of k over square root of n, okay, or in terms of sample complexity, square root of k over alpha squared. And the algorithm is very simple. On each query, it's just going to add a little bit of noise to the output and return the noisy answer to the analyst. Okay, so it's, in some sense, the analyst is for themselves adding noise to their queries. And it turns out that, let me slow down. So what we're going to do to prove the thing we want, we're just going to try and analyze, well, how well does this do in terms of differential privacy, and how well does it do in terms of sample accuracy? Then we can use that transfer theorem to put the pieces together. Okay, so the lemma is that if we add Laplace noise about epsilon over square root of k to each of a sequence of k statistical queries, then indeed we get sample accuracy on the order of about square root of k over epsilon n. Okay, so that just follows by the composition lemma that we had in the previous, that had a number of slides back. So this algorithm is, epsilon prime, I'm adding parameter, I've got parameter epsilon prime at each step, and the epsilon primes add up in sort of the square. What I get, the final guarantee I get is like square root of k times epsilon prime, which is epsilon, so that's what I want. And the sample accuracy I get is about square root of k over epsilon n plus some other stuff. And now if I just apply that transfer theorem, what I get is that the worst case population accuracy that this process will give me is square root of k over epsilon n plus the epsilon that I lose when I'm translating from sample accuracy to population accuracy. Okay, and now all I do is I pick the right epsilon to minimize this sum, and then what I get is the square root of k over n, which is fourth root of k over square root. So again, at a high level, what's going on, I'm just taking some well-understood process whose stability guarantees are easy to analyze and whose sample accuracy is really easy to analyze. And I'm sort of getting out of this whole machinery for free, or at a cost of epsilon, I'm getting a guarantee on the population accuracy, on how much I could overfit. And relative to, say, sample splitting, which we talked about a long time ago, or just providing the straight empirical answer, the big win is I've bought myself an extra square root in the dependency on k. So I went from square root of k over square root of n to fourth root of k over square root of n, which is a significant improvement when I've got lots and lots of queries. Okay. And it turns out that sort of quadratic improvement that comes up over and over again in the applications of these types of results. Yeah, John.
So just to help me contextualize things, so if we were to use like a zero concentrated differential privacy type thing, do these arguments simplify because we no longer need to track around these sort of one on delta things?
Yeah, you get much cleaner statements.
Go through
yeah.
Nicely. Is there any reason why we shouldn't just use those for these kinds of results?
The short answer is no. The sort of longer answer is in a tutorial that requires like more definitions. Okay. So that is the reason I did not do that. But yeah, so actually Om Thakkar, who's like not in the room right now, but is a student at BU, will hopefully give a talk on some sort of more experimental stuff we're doing with Aaron and Ryan Rogers, trying to track like how do you get the best concrete bounds out of this process. And generally, the best bounds you're going to get are like mixing and matching these sort of various notions of stability and these arguments in a few different ways. So,
do we have any, say, hope of some kind of asymptotic argument giving exact constants or something like that?
Not currently. So right now we have in some regimes matching asymptotic upper and lower bounds, but
There's numerical constants that are big.
there are numerical constants. Actually, no, they're like 2. If you try to optimize everything, they're not that big. But that doesn't, yeah. We don't really understand when they're big. So, okay, sometimes they're like 2, and sometimes they're like 50, and understanding, yeah, 2 and 50 are indeed different numbers. Yeah. All right. So just quickly, Aaron mentioned this sort of reusable holdout idea. He said we could answer K queries with error nearly independent of K by using this dirty set to generate guesses and some clean like holdout to verify guesses, and when appropriate, set them straight. Okay? And there was this really elegant compression argument that says, in some sense, the cost I pay in terms of accuracy is going to scale not with the number of, only logarithmically with the total number of queries I have to answer, but the sort of the polynomial cost is only going to come in the number of queries where my guesses are wrong. Okay? It's the wrong guesses that are surprising, that reveal information about the clean set. So now what we could do is come up with a version of that where we use, like, instead of using the compression argument, we use these stability arguments. And what we get out of it is we get basically a quadratic improvement in the dependency on n. So instead of the kind of error being whatever that threshold was plus this square root of w log k over n that Aaron mentioned, and I'm dropping even more terms than he had dropped. There's some like log stuff. Then what we obtain is sort of this sort of same numerator, but with like n in the denominator instead of square root of n. And so I just want to explain a little bit about how that works. But anyway, the point is that this guarantee is better than that one, right? That's all you really need to remember. But how does this work? Well, what we need is sort of a stability-based version of that compression argument that said only the wrong answers really matter. So this thing has a name. It's called the sparse vector mechanism. It comes from originally a paper of Aaron and Tim Roughgardens, and also maybe it was sort of worked out in modern form by Moritz Hart and Guy Rothblum. Suppose we have a sequence of statistical queries, and each asks for the average of some bounded function over the data post-adaptively, same setup as before. And now we just want to know, rather than knowing the values of all the queries, we just want to know those values that exceed a certain threshold. Okay, so in application, what I'm actually going to apply it to is like the difference between a guess and the true value, but like that doesn't really matter. Okay, just imagine I've got a threshold. Each of the queries I want to compare to that threshold. And I'm going to sort of say nope. And wait, I forget which one was yes and which one was no. I'll say one thing if they're above threshold and another thing if they're below threshold. And it's the above threshold ones that are surprising. Was that yep or nope?
I think yes is yep and no is no.
Right, but is yes above or is no below? Okay, good. Thank you. All right. Okay, so here's the mechanism. So actually, I'm cheating a little bit. I've simplified it to the point of being technically not correct, but like morally correct. So this is the morally correct version of sparse vector. I've got a data set X and this sort of sequence of queries coming along. And now what I'll do is I'll just sort of track how many times I've raised my flag and said, oh, you're above threshold. And as long as I haven't raised it W times, I keep going. And basically, for each query, I'm going to add, what I'm going to do is add noise to the query answer on my data. I'm going to add noise to that, and I'm going to compare that to the threshold. Okay? So what I'm doing is just a noisy version of that threshold check that was in the guess and check thing that Aaron described. And effectively what this says is, like, if I'm far from the threshold, I'm essentially guaranteed to do the right thing. If you ask me a query that's right near the threshold, maybe I'll give you the right answer, maybe I won't. You don't know. Okay? And whenever I'm above threshold, I raise a flag, wave my hand, and the flag counter goes up, and otherwise I just keep going. Okay, and again, the theorem, which applies to the correct version of this, not exactly to this, is that if I set epsilon prime to be about epsilon over the square root of the number of bad things that can happen, right, W, then I get an algorithm which is overall differentially private, and it is correct with high probability for all those queries that are not super close to the threshold. Okay, so now I have this additional source of error, which is like corresponds to the sample error in the transfer theorem. So this is going to be, some source of error, which is where the things go wrong. Okay, I'm going to sort of skip over. Sorry, I'm running out of time, so I'm not going to go over it too much, but good things happen. Okay, so for the compression analysis, for the median mechanism that Aaron mentioned, you can sort of do the same. I'm not going to work through it. You can use same ideas. You go from like some dependency on, 1 over 4th root of n down to 1 over square root of n. If you use these different tools. For the ladder algorithm, and this was worked out in a paper of Moritz called Climbing a Shaky Ladder, if I have the right title right. I have it in terms of sample complexity here because I think it's sort of easier to see what's going on. Here you're going from a dependency on alpha cubed down to a dependency of, like you're buying yourself a square root of alpha in the accuracy guarantee. And sort of similarly, a lot of these places where compression algorithms are, this compression-based analysis can be used, such another algorithm called multiplicative weights, you get kind of a corresponding improvement. Okay, so what I tried to convince you of is that sort of privacy and stability are sort of intimately connected with generalization. We can use that in various interesting ways. And in the we started late, but the minute I have left, I want to just convince you that there's also a connection to information theory. And I'm going to kind of punt to other talks to make this connection more explicit. Hopefully, Vitaly Feldman and Max Roginski will say more. But let me just sort of sketch that connection. Okay. So again, here's our little two-stage game where the analyst sees one output from an algorithm and produces a query. And now we want to analyze this game, but using a different sort of way of, rather than thinking about stability, using like a different kind of mental model. And the thing we're going to do is to try and explicitly measure the information in the output that the output conveys about the input data set. Okay, when the input data set is chosen, IID according to P, some known distribution P. Okay, so there are lots of ways to measure information. You've probably heard of Shannon's notion of mutual information. So that looks at the expectation of this log odds ratio, where you're looking at the probability that the output would be Y conditioned on a particular data set X compared to the probability that the output would be Y conditioned on nothing, averaged over all data sets X. So that's like a you may have heard it. That's usually called mutual information. And there are other variations on this. There's something called max information, which is a high probability bound on this ratio. There are various other notions, like you could look at some expectation over Y over the supremum over X of this ratio, and various other things. You can look at moments of the ratio. Those are called Renyi divergences, measures of Renyi information. And so what we can get is, based on a variety of these measures of information, we can get different kinds of guarantees on, again, how well the analyst can do in this game. So just the way almost all of these play out is that what we find out is that the score of the analyst in this game is bounded, roughly speaking, by the square root of the information that's leaked over n. And so the first theorem I know that was like, well, I guess this sort of appeared, there were two papers in 2015. There's one of the Dwork et al. Papers, and also Russo and Zhou, that proved statements of this flavor. And these things we can connect them to this sort of stability-based approach and also compression if we can connect stability to information. Indeed, you can. So for example, if an algorithm is epsilon delta differentially private, then some approximate version of the max information is bounded by about epsilon squared over n. And if an algorithm is compressible, if its output is compressible to L bits, then somehow L got changed into K, then the max information is bounded by L. And if I just sort of plug these two theorems into this meta lemma, I get, again, the types of statements I had earlier in like, everything works out. Like if I plug epsilon squared n into this statement, I get that the score is bounded by epsilon, which is exactly what we had before. Okay. So we can reinterpret a number of these stability-based guarantees in terms of information, and that gives us extra flexibility when designing algorithms. And there are sort of ways this comes up that I'm not going to go into. But I want to give you one very specific connection, which is with hypothesis testing. And I want to kind of go through this because it's relevant to the types of questions that get asked in many of the papers on selective inference in the statistical literature. OK, so let's consider, I promise this is my last technical slide. Let's consider an analyst that instead of choosing a weird statistical query, is choosing a hypothesis test. Okay, so an analyst sees the output of some process based on a data set, and now formulates a conjecture about the probability distribution that might have generated that data. Okay. And that conjecture will be a set of, like, it'll be a predicate on the distribution P, so a set of possible distributions. And the sort of normal way we analyze this is say, well, we'll look at what's called the significance level of the test. So this is the probability that my test rejects. So it'll choose the analyst chooses a statistical test. So that's just like a binary function on the binary valued function on data. Normally the thing we'll be concerned with is the probability that the test would output 1, which is called rejecting, given that the hypothesis actually satisfied the conjecture and that the data set were selected according to the hypothesis. Fresh data set was selected according to the hypothesis. Okay? So there's some sort of soup over P hiding in here. Okay, and so let's call that P0. So let's say I've got an analyst which will always choose a test and a hypothesis whose level of significance is P0. So 5% if you're submitting a paper to Nature. What can we do? Well, one simple thing is to look at them. You can get other formulations of the statement, but this one you can prove like on a napkin. So it's like easy. So suppose I had a guarantee about the max information between the algorithm A and the data set X. Then I could actually use it to sort of bound how bad the kind of possibility of a false acceptance is, even when this conjecture was formulated adaptively based on the output of the algorithm. And specifically, what we can say is that if the mutual information is at if the max information is at most k, then when I additionally condition on the fact that the test was chosen as part of the output of A, the test and H0 were chosen as part of, based on the output of A, then this probability of bad stuff happening goes up by a factor of at most 2 to the k. Okay. And the proof of this is like 2 lines. It basically is just based on the fact that this odds ratio is at most 2 to the k. There's a log missing. I'm sorry, I lost a log. There should be a log like right there. Okay, so what does this tell us? It tells us that at least max information, and there are similar versions for other notions of information, you can think of it as a measure of like how distorted the conditional distribution on X is by the fact that you've revealed this output A. And because you know that it wasn't distorted too much, I mean, it could have been distorted a lot, a factor of 2 to the k if k is big, but it's a big factor. But it's finite, and it's something you can write down.
And can you compute k?
Can you compute k? I mean, for various algorithms, we can prove stuff about k. Yeah, we can prove bounds on k. So in particular, OK, maybe I won't go into that. But for example, for these algorithms that are compressible that Aaron mentioned, or algorithms that satisfy various stability notions, you can definitely prove mutual information bounds and other types of information bounds. And in fact, there's a few recent papers, and I don't want to say author names because I'll get them wrong, that make sort of look at other types of algorithms whose information leakage can be bounded. Learning, like say, learning and statistical algorithms. But basically, what information, these notions of information very explicitly connect these sort of stability type perspective with the kind of conditional inference perspective that comes up a lot in the stats literature. Okay, so that's what I talked about. We concluded adaptive inference is everywhere. There's a great quote: "All inference is selective." I forget who I should attribute that to, but it's certainly true. It's hard to find settings where you're not making conjectures based on things you've noticed about the data, for example. We can get non-trivial results for arbitrary analyst behavior using these notions of stability and information. And one thing to point out is that these give us, in addition, these give us sort of two-sided guarantees. In addition to sort of allowing us to write algorithms that guarantee a certain level of statistical validity, you can guarantee ahead of time that you're going to be able to provide answers of a given accuracy. So it's not only ex post facto that you can figure out how well you did. You can actually think about it. You can think it through ahead of time, which is a useful thing. I didn't talk about lower bounds, but there are sort of various regimes in which these results are tight, some others in which they're not. And information and stability play key roles. Limitations of the current theory: it's most useful when you've got lots and lots of rounds of interaction, whereas lots of natural statistical settings, you have maybe 2, right? And then the last thing I want to say, there's sort of tons of stuff I didn't talk about that a tutorial could have covered. I didn't talk about lower bounds on accuracy and the sort of exact regimes in which we know they work and they don't. I didn't talk about how you get concrete bounds out of any of this stuff. Everything had tildes everywhere and hand waving. I didn't talk about sort of works that have, and there are a few now that have started to think about accuracy sort of as a good, data as a public good. And sort of how do you, suppose I'm the NIH, I pay for an expensive study, I collect a bunch of data. How do I decide like who gets to ask queries, who doesn't? And like how I ration out the kind of value of that data, right? Blake will talk a little bit about that. I didn't talk about models of more benign adversarial behavior. I'll talk a little bit about that tomorrow. And I barely scratched the surface talking about adaptive hypothesis testing. There's much more to say there. So with that, with this sort of caveat on all the, and there are probably others, but a bunch of things I didn't talk about, I will stop. Thank you. So I'm happy to take questions. Yeah, Will.
So can we take the questions then after? I think we're running quite a bit.
Oh, sorry. Yeah. OK. In that case, while I'm